picture this. You're slicing across the water, just a blur, the board barely skimming the surface.
Yeah.
That's a windsurfer, right? And they're often moving faster than the actual wind. How does that even work physically?
Yeah, it seems counterintuitive, doesn't it?
Totally. So today, we're doing a deep dive into the physics behind it. We're leaning on work by Dietrich Hank, an engineer who really breaks down sailing performance using mechanics, aerodynamics, hydrodynamics, the whole shebang.
Right, and it's like getting a peek behind the curtain, you know? Understanding the forces that let someone achieve that incredible speed. So our mission here is to unpack for you how windsurfers push that speed limit, what unique physics are involved, and crucially, where the limits actually lie.
Okay, so what's the secret sauce then? What lets a windsurfer hit speeds that, say, a regular sailboat just can't? The kind that pushes through water.
Well, there are really two main things going on. First, you've got to understand windsurfing is a planing sport. Yeah, planing. So instead of cutting through the water like a displacement hull does, the board actually gets up and rides on top of the surface, like skipping a stone.
Ah, okay. Less contact, less drag.
Exactly. That minimal contact just slashes the water resistance, and that's absolutely key if you want serious speed.
Makes sense. And what was the second thing? You said two key things.
The second big one is how the sail is connected, or rather disconnected from the board. It's decoupled.
Decoupled. How so?
Okay, think of a normal sailboat. Fixed mast, right? Every force on that sail, gusts, shifts, directly affects the boat's stability. It wants to tip it over.
Right.
But a windsurfer uses a power joint, like a universal joint. It connects the rig to the board, but lets it pivot freely. This means the sail's forces, its moments, they don't directly destabilize the board in the same way.
So the sail can tilt all over the place without instantly flipping the board.
Pretty much. It simplifies the stability problem. And that's where you, the rider, become absolutely crucial. You're constantly leaning out, shifting your weight, using your body as a counterbalance to the sail's force.
Yeah.
You're actively managing the equilibrium.
So I become the balancing mechanism.
You got it. And here's a wild thought. The maximum force that sail can actually generate and that you can use, it's limited by your body weight and how far you can lean out your leverage.
Wow. So my own weight literally sets the power ceiling. That's
Yeah.
quite direct. Okay, so you're harnessing this wind power, but it's not just the wind blowing across the beach, is it? There's this thing called apparent wind. What's that about?
Yes, apparent wind. Super important. It's the wind the sail actually feels. See, it's not just the true wind speed and direction. It's a combination, a vector sum, of the true wind and the wind generated by the board's own forward motion.
Okay, like when you stick your hand out a car window.
Yeah.
You feel wind even on a still day.
Exactly like that. And as the windsurfer goes faster, this apparent wind changes. It gets stronger. But critically, its angle changes too. It feels like it's coming more from the front.
More head-on.
Yeah. And as that angle gets smaller relative to the board's direction, the sail becomes less efficient at generating forward thrust. There's an inherent limit to how much power you can extract as your speed climbs, and that apparent wind shifts forward. It's a fundamental physics constraint.
Got it. So that leads us to top speed, right? The point where the push from the sail perfectly balances the drag from the water and air.
That's the equilibrium point. Thrust equals drag. And the calculations, Hank did show something fascinating about how speed scales. A windsurfer's top speed potential is related to the cube root of the rider's body weight, plus other design factors, times the wind speed.
Cube root. Okay, so weight matters, but maybe not quite as much as you intuitively think. But it still means heavier riders have an advantage.
Generally, yes. Heavier and often taller riders who can get more leverage, can handle more sail force, and thus have a higher top speed potential, all else being equal. It's about that balance we talked about.
And what about the drag side of that equation? Where does the resistance actually come from?
That's another really interesting breakdown. You might be surprised. Almost half, nearly 50% of the total drag comes from the board itself moving across the water.
Wow, half. Okay.
Yeah. Then about 30% comes from aerodynamic drag on the sail rig. And the rest is split roughly between the rider's air resistance, maybe 10%, and the fin's hydrodynamic drag, another 10% or so.
So board, sail, then rider and fin. That really shows where you'd look for improvements or where things can go wrong.
Absolutely. And it also explains why record attempts need perfect conditions, like that channel in Lüderitz, Namibia, where the current record, 53.37 knots, was set. It's incredibly flat water.
Because chop would increase board drag massively.
Hugely. And smooth water also helps prevent fin cavitation. That's when the pressure drops so low around the fin that the water basically boils, creating little vapor bubbles. It causes a sudden loss of grip and a big spike in drag. Kills speed and control.
Okay, 53.37 knots is just staggering speed on water. But it sounds like, for a windsurfer, specifically this kind of setup, we might be getting pretty close to a physical wall.
I think that's fair to say. We're definitely pushing up against the limits inherent in the windsurfing concept, mainly because, as we said, the sail force you can handle is tied directly to the rider's weight and leverage.
So to go significantly faster, you need a different approach.
Exactly. If you look at other craft, like Sail Rocket 2 or some of these experimental kite-powered hydrofoils aiming for crazy speeds like 80 knots, they use entirely different engineering principles. They have structures, often hydrofoils, designed to actively counteract the massive turning forces from the sail or kite. They're essentially engineered around that rider weight limitation that defines windsurfing.
They've changed the fundamental game.
Right. They've moved beyond the pure windsurfing concept.
So pulling back from the specifics, what's the big takeaway here? What does this deep dive into windsurfing physics tell us more broadly?
I think it's a brilliant example of how achieving breakthroughs in any field, really, often comes down to first deeply understanding the fundamental physical limits you're working within.
Knowing the rules before you can figure out how to bend or break them.
Precisely. Windsurfing speed is ultimately capped by rider weight and drag. To smash those limits, you need a fundamentally different design. It makes you wonder, doesn't it, what seemingly simple systems in your own world, maybe at work or in a hobby, are actually bumping up against some kind of invisible, physical, or systemic limit that no one's really identified yet.
A great question to ponder. What's the real bottleneck, and what would it take to engineer a way around it? Fascinating stuff.